Welcome back to this fifth lecture in this series on concurrency, state models, and design patterns. Today we're going to be looking at liveness. The outline for today is as follows. First, we'll have a look at what the definition of liveness is, and in particularly we'll look at the notion of progress properties and how they're supported in LTSA. Then we'll look at a classical example of a liveness problem, perhaps the most famous one, and that's of deadlock. We'll be looking at deadlock in the context of the dining philosopher's problem, which is a classical and very well-known toy example of deadlock, but which illustrates very many important issues in concurrent programs. In the second part of today's lecture, we'll be switching over to some design patterns in Java that will support the implementation of live solutions to concurrency problems, and in particular we'll look at different forms of guarded methods. So first, let's have a look at the definition of liveness and progress properties. So we saw before that safety can be thought of as meaning that nothing bad happens, and safety properties express the good things that should happen. Liveness, on the other hand, says that something good eventually happens. This is important because the most trivial way of having a safe system is to simply not do anything. So by not doing anything, you ensure that objects don't get into a bad state. On the other hand, you don't do any useful work. So it's not enough to have safety, you also need liveness. So how do you express liveness? Well, there are various ways, but there's a particular notion of a progress property that we'll see in LTSA, which asserts that it's the case that a certain action or set of actions are always possible and will eventually be executed. This is a weak notion of liveness, but it's strong enough for our purposes. Progress is the opposite of starvation, which means that a certain action is no longer possible at all. So that means that action never will get executed in the future. As I said, a program may be safe, yet suffer from various kinds of liveness problems. So in particular, starvation has nothing to do with safety, but it's a liveness problem. So starvation is also known as indefinite postponement, and starvation doesn't mean that the program stops, but some parts of the program will. Some individual processes are not able to make any further progress. So perhaps most of the system is fine, but some portion of it gets stuck. Dormancy is the case of a process that's waiting that it fails to wake up. This can be the case in Java, for example, if a process, a thread that's runnable becomes not runnable, that is by performing a wait, a sleep, or blocks on I/O, that never gets woken up. That means, for example, if it's waiting, it never receives a notification from another process that the guard condition has changed, or if it's blocked on I/O, that input never arrives. Premature termination means that the process is killed, perhaps by another process. And deadlock is a very particular situation when we have two or more processes that are waiting for each other in a cycle. We'll see that in more detail a little bit later today. Now, progress properties assume a concept which is known as fair choice. Fair choice is a fairly weak notion of fairness. It says that if I have a choice over a set of transitions, actions, an infinite number of times, then every transition in that set will eventually be executed infinitely often. So if I have a coin and I toss it an infinite number of times, I would expect that both heads and tails would be chosen infinitely often. So this is assuming fair choice. Now, I could have a trick coin that 99 times out of 100 will come up heads, and only 1 time out of 100 comes up tails. But this is still fair in the sense of fair choice, because the tails will eventually always be able to come up again. That is, I'll still have an infinite number of tails. So, as we can see here, fair choice has nothing to do with probabilities. Safety and liveness are quite complementary. We saw already that safeness can be thought of as a kind of a process that it can compose with the system transparently. And this property expresses that certain sequences of actions are always possible. So safety for the coin is not terribly interesting. It just says that, well, I can do a heads and I can do a tails and I can repeat that. These are not very interesting. Now, what I really want to do is to state something about liveness. And what does that mean? So progress property is expressed very, very simply as a set of actions which that in an infinite execution, at least one of these actions can be executed infinitely often. Not all of them, any one of them. So I have here, for example, a progress property heads, which contains the set with single action heads, and the progress property tails, which contains the single action tails. So if I have now a regular coin, which I can toss, it comes up heads or tails, and I go to LTSA and ask it to check the progress properties, it will tell me that there are no progress violations detected. That is, heads can come up infinitely often and tails can come up infinitely often. So here we are back again in LTSA. Here we see the regular coin, which we can toss. It has its safety property, which is, as we saw, not terribly interesting. We can compile it and draw it as usual. So here we can see the coin. Here we see its safety property. We can check the safety property, which is perfectly fine, but we can also check for progress. And again, LTSA is a model checker, do an exhaustive analysis of all the reachable states. That's not very hard work because it's a very small label transition system, and it will see that it's always possible, no matter how often you execute this, you always can eventually do heads again, you can always eventually do a tails again. So heads and tails independently are both executable infinitely often. Now recall our trick coin. So if we have 2 coins and we initially pick one of them, we might end up with the regular coin or we might end up with the trick coin. And in this case, we have a problem because, of course, if we pick the trick coin is always going to come up heads, and the progress property of coming up tails will not be satisfied. Now, look at this diagram. We have so-called terminal sets. So a terminal set is a set of states in the finite state process from which you can never exit. So here we see if we pick the trick coin, then we end up in this set of states, and there's no way of getting out of here. We can mutually go back and forth between states 1 and 2, but once we've entered this group of states, we're stuck there. So this is a terminal set. Similarly, if we initially pick the state 3, we can move between states 3 and 4 and 5, but we can never get out of here. So this is a second terminal set. The terminal set of states is one in which every state is mutually reachable, but no transitions lead out of the set. Now, what's important is that some of these terminal sets may satisfy certain liveness conditions, liveness properties, and others might not. Now, if we do the analysis, we see that if we end up with the trick coin, then the progress property, tails, will fail. So LTSA does an exhaustive analysis. It sees where you can end up, what are the mutually reachable states, and checks all of the properties. And notice we have another progress property here, which is heads or tails. The heads or tails property says infinitely often I can choose one of heads or tails. I don't care which one. Now with the trick coin, I can always pick something from this set. It always happens to be heads, but that's fine. So this progress property is satisfied by the trick coin. The only one that's not satisfied is this one. Now, as before, when LTSA does its model checking, it does the exhaustive analysis, and it either proves that the property is fulfilled, or if it's not fulfilled, it generates a counterexample. Here we're back in LTSA again with the trick coin. We have our 2 coins, and we pick one or the other. And we also have the 3 progress properties. Now if we check for progress, it will do an analysis and it will say, if you do the following things, you pick, and then you end up in the terminal set with toss and heads, then the actions that are possible are only heads and toss. And as a consequence, you fail the progress property tails. So in other words, at that point, you're no longer able to execute tails infinitely often. You're not able to execute them at all. And we can see that quite clearly in the diagram here. So we do a pick, we end up in this terminal set, and we're stuck. Now here we can go back to safety, and safety can help us out here. We would like to be sure that we can always pick another coin. So this property repick says that we would like to be able to pick and toss rather than simply pick once and then continue tossing. So this is the repick property. Obviously, this property is not satisfied by the system. So here we've now enabled this repick property, and if we check our safety, it will find that this property is violated, and it's violated quite quickly. We pick, we toss, and we perform, we come up heads, and then we toss again. We cannot pick again, so we're violating this safety property. Now, a question for you is, what will we need to do to change the system to ensure that the repick property is satisfied? We'll discuss that when we have the interactive session later on. Now let's have a look at a particularly interesting liveness problem, which is that of deadlock. So deadlock is a very particular kind of liveness problem, and in order for deadlock to arise, there is not just one, but actually 4 necessary and sufficient conditions for deadlock to arise. First of all, you have to have a set of processes. For these processes to be deadlocked, they have to share some resources under mutual exclusion, and they serially acquire these reusable resources. That means I have 2 or more processes, and these processes are sharing multiple resources. One grabs one, the other grabs another, and then they try to grab the one that the other one has, and they're in a deadlock situation. So we have resources A and B. I grab A and want B, but you've already grabbed B and you want A, and we're deadlocked. Second of all, we have to acquire these resources incrementally. If I can grab both A and B at the same time, then there's no problem. The point is that I'm grabbing first A and then I'm waiting to grab B before I can continue. This incremental acquisition of 2 or more resources is absolutely necessary for deadlock to occur. Third, there has to be no preemption. So if I've grabbed A and you've grabbed B, and then I can say, hey, give up B, let me have it for now, okay? And I'll give it back to you later. And you say, oh, okay, I'll back up, I'll interrupt, I'll give you B, and you can continue running. Then the deadlock is broken. So if there's no preemption, then we can have a deadlock. If we can somehow interrupt some of these processes and force them to give up some resources, we can solve the deadlock in such a way. And finally, as we've seen, the deadlock occurs if and only if we have a waits for cycle. That is, I've got A and I'm waiting for B, you've got B and you're waiting for A. So there has to be at least 2 processes, but there can be more. and each process holds some resource which the successor in the cycle is waiting to acquire. As a consequence, if we have all 4 of these conditions, then we have a deadlock. But if we can break any one of these, then we have no deadlock. Here we have a classical waits for cycle. A has resource A and is waiting for B. The second process has B and is waiting for C. The third one has C and it's waiting for D, and so on. So they're all waiting for each other. And typically they're oblivious. They don't realize that there is a deadlock. How can we analyze this? For the purposes of LTSA, deadlock simply means that we've reached a state in our finite state process where there are no further transitions possible. So this is not exactly what we call a deadlock situation, but this is a deadlocked state. So in order to detect that there's a deadlock, we may have a collection of processes that we can compose, and if these processes eventually reach a deadlocked state, then that's an indication that there may be a deadlock. So for the purposes of LTSA here, we have a process here, which is a robot. Maybe it's a Roomba, and it can go north and south, but if it goes north twice, then it ends up in a cul-de-sac and is stuck and it can't go anywhere. So the robot stops and it's in the deadlocked state. Once again, we can ask LTSA to perform the analysis, and if it finds a counterexample to the liveness property that we want the system to continue to be able to execute forever, then it will generate an example. So here it says it's a progress violation for these actions. The actions that we want to always be able to perform are north or south, so the robot should be able to continue moving. But if we perform north and north, we end up in a terminal set from which no further actions are possible. So this is the progress violation that's violated. The actions that our process should be able to perform, north and south, are no longer possible. Now, the dining philosopher's problem is an artificial problem, a toy example, a mathematical example, but it illustrates very nicely a large number of very important problems that arise in practice in concurrency and in concurrent programming. Here we have a group of so there are many variants of the dining philosopher's problem. Typically we have 5 philosophers, and they're all sitting at a table and they're eating something. It could be spaghetti, or it could be some kind of meal that they share. And in different versions, the philosophers are using 2 forks, or they're using chopsticks, and they share them. So there may be 5 chopsticks on the table, or 5 forks, and the philosopher, in order to eat, needs both utensils. So the philosopher will then grab a left and a right fork, and then use them to grab the food and can eat. And when the philosopher has finished eating, he puts down his 2 forks, or his 2 chopsticks in other versions, and then he thinks. So the philosophers are either thinking or eating. Now the problem, of course, is there are only 5 forks or 5 chopsticks, and no 2 philosophers can hold the same fork or chopstick at the same time. What we want to avoid in a solution to the dining philosopher's problem is to avoid that there be any deadlock and also any starvation. So we should not get into the situation where all philosophers have grabbed their right fork and are waiting for the left fork and they all starve. And we also want to avoid the situation that, for example, 4 of the philosophers manage to eat and the 5th one is not able to. Finally, we would also like to have some efficient behavior under absence of contention. Here's a situation of deadlock diners. Here the diners are in a waits for cycle where each philosopher has grabbed 1 fork and is waiting for the other. Notice that we are satisfying all of the four conditions. We have serially reusable resources. We need more than one fork. We need at least two forks. We acquire them incrementally. We cannot grab both forks at the same time. We grab one and the other. There's no preemption in this case here. Once the philosophers have each grabbed one chopstick, as we see them here, they don't give them up, so they're really deadlocked, and there's a waits for cycle. Although it's an artificial problem, dining philosophers illustrates a number of very classical and important concurrency, safety, and liveness issues. One is that of mutual exclusion, so every fork can be used by one philosopher at a time. We have condition synchronization. Before you can eat, you need two forks. You can model the communication of shared variables, so the philosophers share forks and can pass them to each other via the table. Or message-based communication. You could have a solution in which the philosophers actually pass the fork from one to the other. You have a notion of busy waiting. You can have a solution in which the philosophers look and see if they can grab both forks, and then they try to do so, and if they fail, they can try again. They can busy wait. Or you can have a blocked waiting solution, a solution in which a philosopher who's waiting for a fork can just go to sleep because he's hungry and he can't eat, and he's waiting for the other philosopher to wake him up so that he can eat. Then there's a live lock situation, so philosophers could grab the left fork and busy wait for the right one, or a pure deadlock, as we just saw. So they grab the left fork and wait for the right one. And we have a situation of starvation, possibly, if we have some philosophers that are faster, and one that's particularly slow, and then several of the philosophers manage to eat, but one just never gets a chance to grab the forks. And we also have the notion of race conditions, because we could run such a system and it might never get deadlocked. And just by bad timing, we might get such a deadlock. So that's a classical example of a race condition. So, of course, we can model dining philosophers in LTSA. Here's a possible version of particular version of dining philosophers. We start with a fork. A fork is something that you can get it from the table and you can put it back on the table. So it just loops around. Then we have philosophers. A philosopher, in order, may either get up and be thinking, or may sit down when the philosopher, when he or she gets hungry and wants to sit down and eat, because he or she can't think without some food. So the philosopher then will first grab his or her right fork, then grab the left fork, then eat, put down the two forks, get up, and think, and then loop around. Now we need 5 philosophers and 5 forks. So here's a solution where we prefix all of the philosophers by a name, philosopher 1 through philosopher, actually 0 through 4. So this is again macro expanded as usual. So we have 5 philosophers, and they're all their actions are prefixed by philosopher 0, philosopher 1, all the way up to philosopher 4. Then we have a bunch of forks, and these forks as well, we'll have 5 of them, and each fork is accessible to a philosopher on the left or a philosopher on the right. So the first fork is accessible to philosopher 1 and philosopher 0, then philosopher 2 and philosopher 1, and so on. Notice that we do some modulo calculation here to generate the right number of the philosopher that has access to this particular fork. So here we have our philosophers in LTSA. There's the philosopher, there's the fork, and we can compose the system. We also have a menu for simulating it. Let's compose the system. It tells us there's a potential deadlock. We'll see that in a moment. Let's see if we can have a look at the system. And here's a philosopher 0. Here's a fork, that's between philosopher 0 and philosopher 4. Here's philosopher 1. They all look the same. And the forks all look the same too, except they are only accessible to philosophers on the left or the right. And here's the composition of all of the diners. And here's a case where LTSA can perfectly well perform the model checking analysis of the system, but it can't draw it for us. It's just too big. We've got over 7,000 possible states, and it would just be a mess if it tried to visualize it for us. So it simply gives up on us. We can perform the analysis, so we can perform a safety analysis and a progress analysis. And here, for example, it will tell us, if the philosophers in sequence each try to grab the right fork, then we'll end up in a terminal set from which no possible actions are possible afterwards. So this is exactly the deadlock analysis that we expected, and this tells us that in this version of the dining philosophers, we're really stuck. Here we can go to the animator, and it will show us the different steps that can be performed in running the simulation. Of course, we can also run it manually. So in our initial state, we can see that each of the philosophers can sit down. So we can pick a philosopher to sit down. And then, for example, philosopher 0 can grab its left fork and then the right fork and eat, and so on. And philosopher 1 can grab his or her right fork, but now he's not able to get his left fork because the other philosopher 0 actually has it still available. Once this philosopher puts the fork down, philosopher 1 can then grab it. So even though we can't visualize the system, we can certainly step through the execution, and we can perform a complete analysis. Here again is the result of the analysis, which shows us that we get in the following concrete sequence of steps into a deadlock situation. That is a terminal set where the actions that we're interested in are no longer possible. Now the question is, how do we solve the deadlock? In practice, there are essentially two fundamentally different approaches to eliminating deadlock. The first one is to let it happen and then break the deadlock. So recall we had these 4 necessary and sufficient conditions. We have them all enabled and we have to break one of them. In this particular case with deadlock detection, we keep monitoring the system. If we see that there's a deadlock, then we will take condition number 3, no preemption, and we'll break it. So we'll actually force one victim to roll back. So in the case of the dining philosophers, we could have a butler who is watching the philosophers, and if the butler notices that there's a deadlock situation, the butler could pick one of the philosophers and say, hey, please, could you put your fork down for a moment? And then the philosopher says, oh, okay, sure, and does that, and then the deadlock is broken. And at some point, that philosopher will be able to continue eating once the forks become available. So this is one approach which is typically used in transactional database systems. Transactions run, transactions have to incrementally acquire database records. If in very rare circumstances there should happen to be a deadlock, then a victim, one of the transactions in the deadlock, is picked as a victim and is forced to roll back and then try again. So a key point in such an approach is it has to be possible to interrupt, to break the deadlock, force one or possibly more of the participants to release the resources and roll back and eventually start again. A completely different approach is deadlock avoidance. So here we have all of the conditions as before, but we try and break one of the other conditions. So for example, we could provide version of Dining Philosophers where the philosophers can grab both forks at the same time. All the resources are acquired at the same time. Or we could modify the behavior of the philosophers so that a waits for cycle could never be constructed. So there are a couple of ways of doing that. For example, one of the things that we could do is we could break the cycle by not having all the philosophers acquire their forks or chopsticks in the same order. If one of the philosophers changes the order and grabs the left fork first, then it's impossible to create a deadlock cycle. So it's enough there for one of the philosophers to do it in the reverse order, or perhaps have the philosophers number the forks and they grab the lowest number fork first. Or we could have odd and even philosophers and the odd ones grab the left fork first and the even ones grab the right fork first. There are many possibilities. Another completely different approach is to introduce a butler, and when the philosophers get up to think, they leave the room. And the butler stands at the door and never allows more than 4 philosophers to sit down. So if a philosopher wants to eat and there are already 4 philosophers sitting down, the butler says, please wait until somebody gets up. So you have a queue coming in. At the table, there are never more than 4 philosophers. It's impossible to create a waits for cycle because we would need 5 philosophers. So these are different solutions. The question, of course, here is how do they avoid deadlock? Can we prove it with LTSA? What about starvation? Is it possible with these solutions that even though there's no deadlock, that some philosopher might starve? And finally, is there a notion of fairness here, another notion of fairness that may not be satisfied? Notice we haven't yet defined fairness. We'll come to that in a later lecture. Now we'll switch modes and have a look at guarded methods in Java and how we can construct solutions to conditional waiting with guarded methods that ensure liveness. So we'll see a bunch of different patterns here. In programming, there are different ways that you can ensure liveness in your code. First of all, you could start with a safe design and then selectively remove synchronization to improve liveness properties. Or, this is more risky, starting with a live design and selectively add safety. I think this is not a good strategy, but it's a possibility. And you can adopt certain design patterns that limit the need for synchronization and analysis. So if you have a tried and proven design pattern that is known to work well, then that simplifies your job. Furthermore, recall the distinction between design patterns and architectural styles. There are also certain standard architectures that will help you avoid cyclic dependencies. Now, the most basic pattern is that of guarded methods, as we saw already in the very first, the second lecture of the series, where we saw how Java supports concurrency. In this approach, we temporarily suspend an incoming thread when an object that's not in the right state to fulfill a request and make it wait for the state to change, rather than balking, as we saw last time. So instead of raising exception, we have the process wait and it will be woken up at a later time. We will return to the bounded counter example as before. Recall the bounded counter is a counter that supports increment and decrement methods, and its invariant is that the counter value will range between a minimum and a maximum value. It'll never go below the minimum, nor will it go above the maximum. The guards for increment and decrement are that the count is in range and can be incremented or can be decremented. With guarded methods, there is, as with all the design patterns, some limited applicability. So one of the key issues is whether the clients can tolerate indefinite postponement. With the use of resources that may perform a wait, there's no guarantee that the thread that's become not runnable will become runnable again. So there's an implicit assumption that it's okay for the client to wake and possibly never been woken up. If that's not the case, then we should use the solution that we saw before. We check the guard condition. If the guard condition isn't fulfilled, we raise an exception. So then it's the job of the client to decide what to do. If the client can tolerate waiting, then we should wait. If the client cannot, then raise an exception. We balk. Second of all, we should be able to guarantee that the required states are eventually reached, that is, by other requests. For example, with the bounded counter, if we try to increment it when it's in its maximum value, and we wait for it to be decremented, that assumes that there is going to be some other client, some other thread, which will decrement it. So we should be able to guarantee that that will be the case by design, for example. So we know that they're matching increment and decrement requests in our system. Or if that's not the case, that it's okay to wait forever. You should also be able to arrange that the things that you're waiting for, you can be notified. So that when the state changes, you're able to issue such a notification. Normally that's the case. So with the bounded counter, all the state information that we need there is within the bounded counter itself. We know whether the count value has reached the maximum or minimum or what, and when it changes. So we have control of that information, and we can issue a notification whenever that value changes. Sometimes in other designs, you need information that's not available locally. Maybe that information is somewhere else. So you're waiting for a condition, but it's not properly encapsulated. In such a case, you may need a different kind of a design. So maybe then you have to do some kind of busy waiting. You have to check these conditions if you can't get notified on them. You should also be able to cope with the liveness problems, which could arise if the waiting threads are retaining the synchronization locks. This can be rather tricky. You also need to be able to construct computable predicates describing the state in which the actions will succeed. This is clearly the case for the bounded counter. But as I mentioned a moment ago, you may be waiting for things which you can't compute because that information is just not available to you. You can only find it out by trying an action, perhaps. In that case, everything that we're seeing here in this design pattern doesn't apply. You need a different kind of a solution. And as I said, all the conditions or actions are managed within a single object. If they're not, if you require multiple objects, you might need a different approach, like transactions. Transactions are great for that because you can try and grab multiple resources and roll back if you have a problem. So here, we're assuming everything is nicely encapsulated. Continuing with the design steps, basically, you apply the Java idiom that we see here in front of us. So this is the classical design. We have some object, some service of an object, and that's a public method which is synchronized. You have a guard, and the guard is constructed as follows. While we're in the wrong state, we wait, and we wait in a try-catch clause because it's always possible from a wait to get an interrupted exception. And then, of course, here you should do something sensible. In the examples I have in the lectures, I always leave that empty because that's a bit out of scope of what we're dealing with. But you should seriously consider what, in a real program, what do you do if you do get an interrupted exception. After the guard succeeds, then you perform the actual request. If your state changes, and that change of state might affect this or another service, another thread waiting in a service for a change of state, then you should perform a notify all. waking up all those threads, and each of those threads will then check its condition again in turn when it gets the lock. Finally, after the notify all, then you can return the result. Obviously, you should design interfaces for the methods so that the class can implement the guarded methods according to different policies. So if you, in the case of the bounded counter, we are going to be experimenting with different kinds of bounded counters that satisfy different kinds of policies. So in that case, as we see here, I define a bounded counter interface. And we'll have many different bounded counters that will implement this interface. The interface is quite simple. I can check the value of the counter, I can increment it, and I can decrement it. I have preconditions. The count should always be between the values, the minimum and maximum values, and should never leave that range. Now, for the guard conditions, we need to define a predicate that precisely describes the conditions under which these actions may proceed. Of course, you can encapsulate this as a helper method, in particular if you have multiple services, multiple methods that have the same guard, then you should take that guard condition and put it in a helper method of its own. Then you construct the guarded wait loop, including that predicate, as follows, in the classical way. Or you could even take this whole code, if you have the same boilerplate code in multiple methods, and encapsulate that as a helper method. Now, when you check the guard conditions, it's possible, but rare, if there's only one possible condition to check in this class, and all plausible subclasses, and notifications are issued only when the condition is true, then you don't need the while loop. But this is an optimization that doesn't gain you very much and can be quite dangerous. So if you're absolutely sure all the methods are waiting for the same thing, and if that condition becomes true and you're woken up from it, then you know that the condition is true, then you don't need to check it again. Then instead of a while loop, you just have an if. However, it's extremely rare that that makes sense, so I do not recommend it. Furthermore, you want to ensure that the object is in a consistent state, that is, that the class invariant is fulfilled. Normally, you do not change any state before the guard condition is checked, nor during the guard condition. Only if the guard condition passes, then may you change state. Because otherwise you have a risk that the object ends up in an inconsistent state while you perform a wait. When you perform a wait, you become not runnable, but you also release the lock on the object, which means another thread could come in and see your inconsistent state. So the classical thing to do is to simply perform the guards before taking any actions, as we saw in the template a couple of slides ago. Now, I mentioned it briefly. You need to establish a policy to deal with interrupted exceptions. As I said, all of the examples that I'm going to show you in this course will just have an empty catch clause, but this is not something that you should do in real code. So there are various things that you could do here, and you have to consider carefully for your application what makes sense. The first thing that you could do is to ignore interrupts. That's what I did, but it's not recommended. So you have safety, but you have possible liveness problems. Another thing that you could do is terminate. You could stop the running thread. This preserves safety because you don't perform any actions, you don't modify the state, but it's rather brutal. That's also not recommended. A thing that's probably the best thing to do in most situations is exit, but raise an exception. So you're saying, okay, I got a problem here. I'm being interrupted for some reason. Who knows where the interrupt came from? I don't know what to do now. It's not my job to decide. It's the client's job. So you raise an exception. So you'll have to define some suitable exception that the client of this resource class can respond to and decide what to do. So this preserves liveness, but it requires the caller to take special action. For example, maybe the client wants to try again later. One thing it might be to clean up and restart at some level, either at the level that you are there or at the client level higher up. Or another possibility, really in an interactive application, is to ask the user what to do. This may be fine, or it may be a completely loopy thing to do. So I think all of these are, depending on whether it's an interactive application or a batch application or whatever, you have to decide what to do in these cases. Now, when the object changes state, then, and the state change is something which is relevant to the guard conditions of any of the public methods, then you need to add notification code. If, of course, the method simply reads the state and computes something, returns a result, but doesn't change the state, then that's not going to affect any waiting threads. So the waiting threads are waiting for a state change so that they can check their guard condition again. If you're only reading, don't do a notify. If you change state and that state change might affect waiting threads, then you really must issue a notification. You'll add this notification to every single method of the class, all the public methods, or if we're using helper methods which are protected or private, you will have to put it in there. So the methods that change the state in the way that might affect one of these guards. Normally, you should perform a notify all. This will wake up all the threads that are blocked and waits for the host object. So they will be woken up by the scheduler in turn. They will all become runnable, and they'll be scheduled, and eventually they'll each get a chance to check the guard condition. If the guard condition fails again, they'll go back to sleep. An optimization is to use notify instead of notify all. You can wake up then only one thread, but the thread, you have no control over which thread it is. If there are multiple threads, then one will be picked by the scheduler, and you have no control which one it will be. This is an optimization that only makes sense if all the block threads are waiting for conditions signaled by the same notifications. They're all waiting for the same thing. And then it doesn't matter which of them becomes enabled. If that's the case, then you're good to go. Notice with the bounded counter, that's not the case. We may have some threads that are waiting for the counter to leave the minimum state, and others which might be waiting for it to leave the maximum state. If I've got hundreds of threads that are incrementing and decrementing the counter, that might well be the case, that some of them get stuck waiting for it to leave the minimum, some waiting for it to leave the maximum. If there's a state change, I should be fair, wake them all up, let them figure out which one can proceed. If that sounds too drastic for you, if you really have lots and lots of threads waiting on the same object, on the same lock, you could implement your own special purpose notification methods, build them up on top of notify and notify all. For example, to selectively notify certain threads or to provide certain fairness guarantees. But that gets very, very tricky, and I wouldn't recommend that unless you have a very, very unusual and special application. So, in the end, use notify all in almost all cases, and very rarely would you do anything different. In all the examples that we'll see of the different bounded counters, we will be checking our invariant and keeping track of the number of errors. So in case there are buggy implementations, we'll track that. So we'll start with an abstract class, bounded counter abstract. It implements our interface, and we have the count variable introduced, and we're also going to track errors just for testing purposes. Here's our invariant. The invariant checks that the count is between the min and max value. If it isn't, what we're going to do is we're going to increment the errors variable so that we can check it when we're debugging or testing. Here's the simplest version of the bounded counter, the basic version. It follows the most basic pattern. We have the synchronized increment method. The guard condition is that the count must not be at the maximum value. If it isn't, then we're going to wait until it is lower, because once it's at the max value, we cannot increment anymore. Once we exit from this guard, then we know that the count is less than max. We're in a synchronized method, so we have exclusive access. We're in our critical section, and we know it's safe to increment the count now. Nobody else can be in there together with us. Because this condition has now changed, this may change the guard condition for other threads. So we must perform the notify all. If we were only reading the count variable and not making any state changes, we wouldn't need to do any notification. So this is the classic basic pattern. For our testing purposes and to compare different versions of bounded counters, we're going to check our invariant here and log any possible errors. Here's a bad implementation of the bounded counter, which is busy waiting. That's one possible bad implementation. Here we have a non-synchronized increment method. It does have a guard, and what it's just doing is it busy waiting. So while the guard condition fails, we're going to yield. So that makes us temporarily, it doesn't turn us into not runnable. We stay runnable, but we just ask the scheduler to schedule another thread briefly. And this has no guarantee that it'll change the guard condition. So we're just going to get scheduled over and over again. What we could do here is do a very short sleep of a millisecond or 10 milliseconds. Then we would become not runnable and get woken up when the sleep period is over. Now at this point, the guard condition is true. So we've passed the guard condition. The count is no longer at the max value. So now in theory, we should be able to increment the count. But we're not holding any lock. There may be other threads which get scheduled. And in order to provoke a race condition here, to increase the likelihood of an error, we're just going to yield here. So that means that at this point, we think the guard condition has passed, and we should be able to proceed with our action, but another thread might be able to get in there. So we're going to test this guy out, and we'll see that we actually will have some problems in certain cases. Here's our interface for the bounded counter. It just specifies the method's value, inc, dec, and errors, and it also defines our constants min and max. Here's our abstract interface, that abstract class which implements errors and check invariant, but doesn't implement our the other methods, increment and decrement. Here's a basic implementation, which uses the classical synchronized method with a guard, a wait guard, and a notification after the state change. And the decrement looks pretty similar. Here we have a test case which tests lots of different implementations. We can, what it's basically going to do is going to run these tests. We have a thread count of 100. We're going to create 100 threads that want to increment, 100 that want to decrement. We'll just let them compete, and we'll start all of them, wait for them all to be finished, and then we'll check and see whether the count is back down to 0, and also that we have 0 errors. So we can run our tests for the basic bounded counter. And we see that everything runs just fine. Here's our bad implementation, which is implemented with the yields and not doing any synchronization whatsoever. We can also try and test this guy, and we're expecting it to fail. Here we have a bit of a problem because we're going to wait for all of these threads to terminate, but if some of these threads get stuck waiting because the counter has ended in a bad state, then the test will never terminate. So we can try it again and try it a number of times. Basically, we can see this is not a very happy test. What we could do is the following: is make use of a conditional breakpoint, and we'll check at the point where we check the invariant, and if the count is less than min or greater than max, then we'll stop. And now we can debug this test. And in fact, we see here we end up with a state where the count is at the value of 6, which is not good. If we remove this test, this one of the two breakpoints, and run it again, then we can even see that the count has gone way out of range. So this is clearly, using busy waits is clearly not a good thing to do. If we eliminate the thread.yields, the situation might change a little bit. But we see that it hasn't. Now it's getting stuck in waiting for all the threads to terminate. Now, with some of our tests, I've been able to demonstrate that certain code is broken by provoking a race condition, but it's not always easy to do. I'd like to convince you that using notify instead of notify all is a bad idea. However, it's very hard for me to construct a Java test that proves that, because I really have to provoke a certain kind of race condition. Instead, what I'll try and do is convince you with this slide here. So here I have 4 objects in a UML scenario diagram. We have a bounded counter BC. That's this guy here. And then I have 3 clients, A, B, and C. First, A tries to decrement BC, but the bounded counter is at its minimum value. So this causes thread A to wait. Now B tries to decrement as well, and it waits. C comes along and increments. The incrementation generates a notification, which will wake up one thread, because we do a notify instead of a notify all. Then C performs another increment, and because now the bounded counter is at its maximum value, here we have a bounded counter that only goes from 0 to 1, then C will wait. Now object B wakes up and finishes executing. It does its decrement and it does a notification. This notification wakes up one thread, and in this particular case it wakes up thread A. But thread A checks and sees that it's at the minimum value because it's just been decremented, and it goes back to sleep. Now we have both A and C waiting, and they're waiting for nothing because there's no thread that will wake them up. If we'd done a notify all instead of a notify, then the first time both A and B would have been woken up, and the second time both A and C would have been woken up, and they would have each had a chance to check the guard condition. The key thing to watch out for is that every single wait should be balanced by at least one notification. So there are several things that you can do, and we'll see implementations of these. The most simple thing to do is to have blanket notifications. That is, at the end of every method, place a notify all. End of every method that can cause a state change. This is simple and reliable, but may have some disadvantages. A second thing that you can do is to be a little bit more clever and encapsulate the operation of changing the variables that may change state. So then, once you've done that encapsulation, that method which does the state change will generate the notification. So again, blanket notifications, you have a notification at the end of all methods that can cause a state change. With encapsulating assignment, we add a new method that encapsulates the changes to the variables of interest and then does the notification after the variable is updated. Now we have a couple of slightly different approaches. Tracking state will issue notifications for the particular state changes that actually unblock waiting threads. So you don't change after all states, but only the interesting ones. This can improve the performance because you generate fewer notifications, but the code may become a little bit less flexible, particularly if you want to subclass. Then a more abstract approach is tracking state variables. So here you have a special instance variable that represents the control state, and we'll see the example in a moment. So in particular, here with these, with the bounded counter, the interesting state changes are when you leave the maximum value or when you leave the minimum value. If I have a bounded counter that goes from 0 to 100, all the state changes in between are uninteresting. Essentially, with the tracking state approach, you would check only when you leave the max value or when you leave the min value, because those are the situations where somebody's going to be blocked. With tracking state variables, you would have an additional variable that models the fact that I'm at the max value, min value, or somewhere in the middle. So there are only 3 interesting states, not 100 states. And the last approach that we'll see is using helper objects to maintain the aspects of the state and have them issue the notification. This one is a little bit more esoteric. So I think the ones that are most interesting, blanket notifications, most of the time, that's going to be perfectly good. So this is the standard default solution. And then these are interesting, can be useful, especially if you have lots of threads waiting for certain conditions. Then you will generate fewer notifications in these cases and wake up threads needlessly less often. And the last one is rather specialized. Okay, let's see how they're implemented. Here's the encapsulated assignment. Now we've abstracted away from, so the implementation is absolutely equivalent to what we had before, but we've abstracted away and our increment and decrement methods are at a much higher level. So we've encapsulated the guards. We have the increment does await incrementable, and then once it's incrementable, then we set the count. The decrement awaits to be decrementable, and then again it updates the count by 1 less. How does this work? Here's await incrementable. It just encapsulates the guard condition, so no surprises there. And await decrementable is similar. Set count is the encapsulated assignment. It is a setter for the count variable that issues the notify all. So there's no big surprises here, and this works perfectly well and as expected. The next approach is tracking state, and here what we're interested in is knowing exactly when we leave the logical states top and bottom. So here's another implementation. We have the guard condition as before. this time not encapsulated as a helper method. And in this case, we only issue the notify all if the previous value of the count variable was at its minimum. So this is an optimization. If we were not at the minimum, then the state change couldn't possibly affect a decrementer. So the decrementer can only be stuck if the count was at a minimum. We've left the minimum now, so we should wake up. We're interested in waking up any threads, particularly those that were stuck at the minimum value. The next approach is tracking state variables. It's very similar, except instead of sampling directly the count value, we are going to introduce an additional abstract state. So the state can be I'm at the bottom, I'm in the middle, or at the top, particularly if the count variable doesn't go from 0 to 5, but from 0 to 100 or 1,000, then the middle is going to be very big. As in the previous solution, we are only interested in when we leave the bottom or top state, but instead of sampling directly the count variable and testing whether it's no longer minimum or maximum, we explicitly check whether we check not the count variable, but the state variable. Here then, for incrementing, we want to be sure that we are not at the top value. If we're at the top value, then we will wait. Once we pass the guard condition, we increase the count, and then we'll check the state. Checking the state requires us to keep track of, to compare the state with the previous state. So here, we store the state, the previous value of the state. We check if the count is now at the minimum. If so, the new state is state.bottom. Or if it's at the maximum, now we're at the top. And otherwise, we're in the middle. If the state has changed, then we perform a notify all. How do we know if the state has changed? Well, we compare the old state to the new state, and if the state is not equal to the old state and the old state was top or the bottom, then we want to issue a notification. So it's a little bit more complex, quite a bit more complex than the previous one. It's a little bit more elegant in the sense that we're modeling these important abstract states. Yet on the other hand, if you want to subclass this class and add additional behavior, then it's going to be very, very hard to extend this code. So it can be interesting to do at times, but I would expect that this is very rarely the right solution to take. The last example is delegating notifications. The idea here is we make use of an additional object which will handle the notifications for us. So now the count is stored in a separate object called the notifying long. We have a set value method here, which will, so it's a setter that will update the value. And now we have the problem that we have two objects that need to be synchronized. We have the notifying long object. So when we update it, we have to synchronize with respect to itself. And we have its observer. And the observer is the bounded counter. And that's the thing that has to be notified. Notice this weird bit of code here. We have to synchronize with respect to the observer, because otherwise we can't issue a notify all, because the notify all only is legal within a synchronized code. And now we have the unlovely situation that we actually have to have two synchronized codes blocks here. Notice there are not two critical sections. The critical section is here where we update the value. The other synchronized block is not a critical section, but it's only there to be able to issue the notification. So this is a little bit complex. Here's how it could be used. We have the bounded counter with the notifying long. The count variable here is an instance of this fancy notifying object for us. And here's our increment method. We have the usual guard condition, and then we grab the value of the count, we increment it, and we set the value. Now it's the job of the notifying count object to actually issue the notification back to us, back to any of the threads which are blocked on us. Notice this is kind of complicated because we actually have two resources. We want to avoid having synchronized code within other synchronized code, which is why we have these two separate blocks. This works fine, but it's a little bit hard to reason about, so I wouldn't say it's a recommended solution. The others are much simpler and much more appropriate. Back to IntelliJ. Here we have all our different versions of the bounded counter that we're interested in testing. The basic version, the encapsulated assignments, the tracking state, the state variables, and the notifying long. Of all of these, I think the encapsulated assignments are relatively straightforward. Here we see that it's simply the setter here which issues the notification. This is more complicated in the notifying long because it's a separate object with its own synchronization. And the other one, which is relatively simple, is the tracking state rather than the state variables. So the tracking state just simply optimizes over the simple solution by only issuing the notifications when we've left the bottom or the top state. So we have fewer notifications, and this should all work fine. Now, of course, if we run all of these tests, we expect, and they all run perfectly well with 100 incrementers and 100 decrementers, and we get no surprises. Okay. That's everything I wanted to show you for this week. Thanks for your attention.